Okay, so in this video I'm going to take a closer look at the InStep Studio 3D version 3.1 bodies options. We previously covered the basic import and the edit tools, so we're going to move on to the bodies tab that's located here. For this I'm going to go ahead and import one of the default test files. It's just going to be the monkey head. That's an often used file in this set of videos. It's an often used file for this set of videos. So let's take a quick look at this. This is just a fairly organic shape, and overall this would be fine as a body. We could directly export and do things like that. I'm going to go through, I'm going to make two quick edits here. We're going to select two facets, one on each of the closed eye sockets, and we're going to flood it up to 10-degree angle limit, and then we're going to delete those facets and we're going to apply that change to the data. So we've seen that in the edits tab. That's nothing new here. Now on the bodies tab though, we're going to take first a look at the shell body section, and specifically the only tool in there is the thicken option. What thicken does is takes existing data and it turns it into a solid thick sheet. The easiest is just take a look at that and what it does. So if we click on that, it brings up our thicken toolbar, and under the method we have local, uniform and to plane. The most commonly one used will be the local tool, and with that we simply apply a parameter as a factor of 0.1 in this case, and that's all it really takes. So we can do a quick preview, and then after just a second this turns light blue, which is the default color for preview data. At first glance it doesn't look any different from what we just saw, but there's a few things I want to point out before we get into a closer look into what that tool does. If we zoom out, we start to see this sort of visual artifacts. That's the black stripes showing up in the background here, and if we zoom in a little closer they don't really go away. This is purely visual, so it's got to do with how the depth of a body is being displayed. We can go to settings, application settings, and we can modify that. So near plane clipping distance and far plane clipping distance are the two. Effectively, how to understand that is, this is the distance from the front of the viewer before data disappears, and this is the back distance. So how far away from the view surface can you go before it disappears? In general, these are defaults that work for most scenarios. In this case here we're seeing some artifacts, and that's got purely to do with how close the inner surfaces are from the front to the back, so it can't really distinguish. If we wanted to get rid of that, we could just change this to a larger number, say 0.1, click OK, and then we go back and redo this, and now we actually see those disappear. Effectively what's happening within the algorithm is actually it limits that distance from the near plane to the far plane, and there's a number of divisions within that where it can distinguish what is one side and what's the other. So generally you're not going to have to touch that, but if you see these artifacts pop up and you want to work with data that's going to trigger that, then that's a way of doing that. We could do the same thing for the far clipping plane, bring that closer in. That would have a similar effect, but what you'd see is as you zoom out, suddenly it would disappear. Whereas this case, you can zoom in and things still work pretty much the way it's intended to. Those numbers are a factor of how close you are to something. Anyway, that being said, let's get back to the body, and we've done the local thickening with a factor of 0.1. Now if we zoom in on the edge, so what we'll do is we'll turn on rotation points with Alt R, and then we'll middle mouse button click near this section here, and sometimes this takes a try or two. There we go. So that sets our rotation point, and I have a spaceball or a 3D connection device, so that allows me to work with this a little bit more easily. We're going to zoom into that section, and now we're going to turn on the edge mode as well. So Alt and E turns on edges. So now if we look at that, we can see there's a front surface, which is the original body, and then there's an offset, and then there's an inner surface. So by thickening the original sheet, and we can delete that to take a look at what it looked like before, we have this sheet, and what it does is it copies these facets, applies them on the inside with a certain offset. The reason this is a factor, and generally the way you want to do this, it will look at each individual vertex and it'll determine a distance based on attached edges, and then I'll apply a factor to that to determine how far to move it in. So the thickness will vary between different locations. Generally, you think that may not be desirable. You may want to have a constant thickness offset. The reason for this being maybe preferred is that if you have very tight spots, the local offset will still function properly, whereas a constant offset may cause issues. That being said, we do have the option of doing a uniform offset, and now this turns from a factor into an actual distance. So if we do a preview, and we'll zoom out a little bit to actually show this better, we can see that 0.1 is actually too far. Okay, so with an offset of 0.1 for this size model, and it is set to being a very small model, the distance is too far and the facets don't properly align anymore. So for this we may have to go a lot smaller. So at this level you can actually see that the offset is uniform in thickness and small enough to still prevent collapses in probably most of the locations. There's an extra option here which says use quads. That's only got relevance to how the offset method is applied where new facets are being introduced. So these sections here, that's just two triangles, but if we use quads, it comes up as a single quad element. Overall, not a big deal. I would generally recommend you leave it to triangles if you're going to work with triangle data. As it is now, if you have triangles and quadrilaterals, or quads for short, you actually end up with a mixed set of data, so other functions won't be applicable to that. So leaving that off is generally the way to do it. Now I'm going to use the home button, which will just jump out so we can get a quick look, and you also see that the rotate center is being reset. So home button resets the view, and if you did control and home, it completely redraws the data. You'll see a little animation of the progress bar changing down here if you do that. The last option in this is to plane. This is probably the least used. What it does is it doesn't extend the thickness to a locally determined direction, but it applies it to an entire plane. So for this case it doesn't make much sense to do it, but I'll show what it does anyway. If we do corner plane, I will choose the XY plane. If we do an apply, it's just going to drop everything to that XY plane. So top down and bottom up as well, which is why we get this sort of sheet here. That's not going to help in a scenario like this that we're trying to thicken a body, but it might be applicable for cases where we have a topological or topographical map of something that we want to actually turn into a solid piece. We could use this and apply thickness to it. Okay, so that's the thicken body tool. Let's take a look at the simplify. And for that I'm going to go back and I'm going to do import, and we're just going to do a recent. So that's the samples monkey file that just reloads it. So we're back to the version that has the eye sockets filled in. Simplify is pretty much exactly what it sounds like. We can simplify the data, or as it says here, simplify, reduce the count. If we look at the information on the side here, we see it's got 13,924 features. In this case, each feature is just a triangle. We can drastically reduce that. This tool is quite capable of going down to some really small numbers. So we have a sizing method. We can do absolute, or we can do a percentage. And a percentage is just, do you want to go half the size, quarter, whatever, of the original. Absolute will try and hit this target size. If I set it to 1,000, so 13 or 14,000 down to 1,000, that's quite drastic. So we can see the overall shape remains, but all the triangles are drastically reduced in the count and obviously made bigger to fit the shape. We can go very low, so I don't know what the lowest number we can go to still recognize it, but even at 100 you can see some of the original data is being represented by this count. In general, for something like this, I think reasonably you're probably looking at somewhere about 2,000 is a good number. But often, especially if you do 3D scans, that data can be very point dense in areas where there's very little going on, so you can drastically reduce that data set. And it's something I often recommend when people work with scan data, is to actually reduce it to a reasonable amount first. And you may just say, rather than absolute, let's just take a target of 10%, so that'd be 13 or 1400 or 1400. You can see that is actually quite realistic in this case, at 10% of the original. Lastly, the coordinate grid method is very different. It doesn't just reduce the number of facets, actually tries to collapse locations together and then finds an average. So this would be applicable in cases where you may want to use integer grids. So for example, right now it's 0.01, but if you wanted to use a grid that's a span of 1, obviously in this case can be very blocky, but let's take a look at that anyway. It collapses to 0. So let's take a look at 0.1. You can see it sort of pixelates the data to some extent. Is this particularly useful for this kind of geometry? I'd probably say no. It does have its uses in some cases, and those will be very specialized, but it is an option that's there, and it can be used. What I should mention is the absolute and the percentage method will retain facet continuity, or the overall topology of the data, whereas the coordinate grid method may actually cause collapses like you can see here on the edge. That's generally tried to be avoided with the other methods, but in this case it's not guaranteed. So we're going to reset that. Let's talk about the next tool, the subdivisions. Subdivision is pretty much what it sounds like. It takes a triangle and it divides it down. So in this case, if I click on that and bring up the tool, we have the original about 14,000 triangles. If we do one iteration, the number of triangles will increase, whilst at the same time also increasing the smoothness of the surface. Generally, that's not what we want to do. So in this process of working from a STL or OBJ file, trying to convert that to a CAD suitable format like STEP, we actually want to keep things as coarse as possible, whatever we can get away with. This is sort of counter to that. It tries to make things smoother. So with one iteration, we do a preview. This can take very long, so be careful when you start increasing these iterations. But you see the overall body is actually smoothed out now, so some of these rougher features have become a lot smoother. And if we take it one further, so now we have 334,000 facets. Again, this will take a second. We now see this body, and And really what it does, it just takes each original triangle and looks at the normals at all of the corner vertices and tries to create a more uniform division of that. I'm going to cancel out of this, and I'm going to import a very basic cube. So I'm going to go open, import cube. Let's take a look at what this does, because there's something to be pointed out here. With subdivision, and obviously it starts off with 6 sides, 12 facets, we can increase that quite a bit. So let's go to 6 iterations and do a quick preview on that. What's interesting to point out here, this doesn't slowly start approximating a sphere. It has some of the original data inherent in it, and that's got to do with the specific algorithm. So you can't simplify a cube down to a sphere. That's not the kind of rounding we do. Okay, so next thing to look into is the tri-quad tool. We'll go back to our monkey model, and the tool comes up with default options again. What this is designed to do is designed to transition between triangles and quadrilateral shapes. Generally, this won't be needed. However, there are some cases where a quadrilateral representation is actually preferred, and not just because there's half the number of triangle or half the number of features in it, but it does actually have some underlying uses. The tool itself is very straightforward. There's no actual options to choose other than the method. Pure triangles, so if you started off with the data and you brought it in and it's in quadrilaterals, the pure triangle option will literally just split each quadrilateral into a triangle, and it'll apply just a little bit of knowledge of the locations to figure out which kind of split is preferred. But in this case that wouldn't do anything because we're already in a fully triangular mesh, so it says all tris. We can do a quad dominant. And what a quad dominant is, it'll try and combine as many of the triangles into quadrilaterals as possible without getting too extreme. So it'll have an iteration it'll go through, and for each triangle it'll find the best neighboring other triangle to form a quad by. If you started from a quad, split them, and then went back to doing a quad dominant, you would essentially get the same mesh out of it. In this case though, there are some locations that work just fine. So up here you can see, and that's got to do with the original mesh actually being a quad mesh that was then converted into triangle mesh, but it's not always guaranteed. So in these regions you might start to find some that are just still triangles. In this case it worked perfectly fine though, so that would be acceptable. We'll undo that real quick. The split quad is a guaranteed method to get in fact you get 4 quadrilaterals per triangle. So if we apply that, we can see that each triangle has been split up into 3 quadrilaterals, and it's just a geometric method by which we can do that. So you can see this was originally a triangle here, and it gets split up into those 3 quads. It obviously triples the number of resultant surfaces, but at the same time it's guaranteed to work in the triangle to quadrilateral conversion, which is otherwise not guaranteed. The pure quad is an internal algorithm that was developed, and it does just like the quad dominant method. It tries to combine them initially. However, if it then fails to truly combine all triangles, it goes in and does an additional step by which it then forces all triangles to be combined, provided that the original mesh was actually an even number of triangles. Otherwise it's obviously not possible without creating something extra. It does take a little longer. In this case it's fine. What you'll often see with these meshes is that you'll end up in places where the surface doesn't look like it's quite correct, and that's got more to do with the fact that a triangle is guaranteed to be on a plane, whereas a quadrilateral is actually not. And if you see surfaces that look a little out of shape, like here, it's often got to do with the fact that one of the corners may be on a straight line, so it then suffers from proper normal orientation or determination of what the normals are. But that's a useful tool that can be applied to some scenarios. Again, it's not very common, but it is there. And uh, like I said, the quad dominant is guaranteed to function, but it may keep some of the triangles. The split quad is guaranteed to work in all cases, but it does increase the number of resultant surfaces. Now, the remesh tool is interesting in that it can be used for a number of things. What it does is it moves locations along surfaces to try and improve the quality of those triangles. So in this scenario, most of the triangles are actually relatively good. I mean, some of them are quite sliver-like, meaning two of the edges are a lot longer than one of them. This tool will allow us to make those more uniform, and this is probably not the best geometry. Let me open up a different one. So this is an OBJ file, and in this case now you actually see it disappear. So we're going to go back to settings, and we're going to find our near plane clipping distance, and we're going to increase that, or sorry, make it finer, so 0.01 from the one we previously set. And now we can see that. So basically it was being clipped off. And anyone that's seen the first tutorials, you know that's got to do with the fact that this is a really small body. So we're going to go in, we're going to size as if the imported data was in meters. So it's going to scale that by a factor of 1,000. Okay. So this geometry is most likely from a scan. I'm actually not quite sure where it came from, but it was provided by a user. In here we can see some of these triangles are not very nice, so this wouldn't lend itself well to scenarios where detailed triangles are needed. So we can go to bodies, remesh, and then we can fix the boundaries. That's been worked on since the 3.0 iteration. In this case, you can actually see that this is pretty much a flat surface with a clear edge boundary. So we can fix that by setting it to 60 degrees, meaning anything that's got an edge with two facets attached, where the angle is bigger than 60 degrees, will be considered a solid edge that we want to maintain. Project mesh means that once it's done, the original surfaces will be used as targets for projection of the new vertices onto it. The factor has to do with how far each vertex can be moved during an iteration. If you set it above 1, there's a very good chance that facets will become distorted and collapsed and unusable. So I recommend keeping it below 0.5. 0.4 is a good starting point. And the number of iterations just says how many times do we allow it to move, because each move then can introduce new triangles, or not introduce new triangles, but introduce scenarios where the triangle edge is not as defined. So running several iterations is generally preferable. In a best case scenario, you'd make the factor small and the iterations large, so say 0.1 and 10 or even 100. Now, the length option is the target edge length that we want to go to. It's set by default to the average edge, and it's now shown over here what that number is. We can also pick the minimum edge. Be careful with that. Sometimes there's very small edges that you don't see. So setting it to the minimum edge will create a very large mesh. We can also just say maximum edge, that's what we want to go for. Or if you want to type that in and go to value and set it. It will always be set to whatever the last one of these was selected. So in this case, let's start with the maximum edge and see what this looks like. We hit preview, and now we can see, okay, it's trying to get to the largest edge it's found. It obviously does that very quickly because there's fewer. This is probably not desirable, so we're going to go to value, and let's set this to 0.2. do a preview on there, and now we see a mesh that's relatively clean and actually well behaved. We have a few places like here where you can tell that the edge is probably going to cause issues. So we're going to set our rotate marker there, and we're going to increase this to say 20 iterations. Now you see with more iterations that gets refined better and better, and we end up with a mesh that's actually very uniform in scale and look and feel. As I mentioned, the fixed boundary tool prevents these edges from being collapsed. However, with too many iterations it can become distorted where the actual edge is. So sometimes if an edge is very important to be maintained in a certain location, it's actually going to be necessary to set the iterations to 1 and then run the tool multiple times. Another last option here would be if we wanted to keep the topology. This is probably not going to be used very often, but keeping topology means that the original data should maintain, and the only thing we want to do, so we don't want to change vertices, we only want to cut vertices. That's a very rare scenario, so use this sparingly. But if we go to average edge and we see the average edge is probably about 0.4 is a good number to use for that, and we now want to set this to say 0.1, it gives us the option to trim a lot of these down whilst maintaining the actual data that was originally used. And this can be a little bit slower because a lot of the divisions that it would do internally then become cancelled, and it then has to look for a better way of doing the same thing without changing the underlying data. So this obviously took a little bit longer, but what you can see is that the result essentially still maintains some of the jaggedness. So we're not really smoothing it in that sense, but the algorithm has created new facets within existing facets basically. So edges have been split and reduced, and therefore keeping the topology. The only place that really makes sense, and actually the reason why this was developed in the first place, is for finite element meshes where the vertex locations may be very fixed and therefore shouldn't move. This allows some of the elements to be further reduced while still keeping the original surfaces intact. So use this sparingly. It's useful to have, but it's probably not the main intent of this tool is probably not to use the topology option. The project mesh, like I said, just means that the original mesh is used as a place to locate the new vertices onto. Okay, so that includes the facet tools, things by which the facets themselves can be modified. And the reason these are under the bodies and not under the edit is it applies on an entire body basis. So whereas the edit sections really apply more to individual facets or facet groups, this truly does apply to the entire body. Now, when I talk about body, a body is really just a collection of triangles in this case. If I import one that is just a very large number of bodies, so you see it consists of a grid of spheres basically. When you do that, the application will ask you if you want to split this. Generally this should be yes, unless you have a very specific reason. So you can make this the default, so you can turn on make this default and then click yes. So anytime you import a data set, it will try and split them up. Clicking that will split them up. Okay, so it will determine that there's individual bodies here. If I didn't do that, so we'll go back, we'll reload this, now we click no, it'll keep it as just one set, and it'll treat it as if it was one body. Several things will become strange if you do that. So some of the edit and repair tools and so on will think that it's a continuous body, but then fail in some operations where continuity is not maintained. Let's say you did this, and let's say you always want the application, just bring it in the way it is, minimize any kind of splitting. We can initiate this manually, so we can go to bodies, and then this is under the Boolean tab. We can do a split, and we can preview what that's going to look like. It's going to be exactly what we had before, and we can do an apply on that, and we get back the same thing we had. However, there's a few subtle differences between using it this way and the other way, and that is that if we import a file that is more geometric in this case, something like this. This is a single body. Okay, so this was a project for a client that didn't work out well. This is a single body because it's a continuous set of triangles. Under the bodies tab, we can go split, and we can actually do something more. We can do by angle, and if we set it to 90, it'll look for angles between two facets that are more than 90 degrees or exactly 90 degrees. So 89.9 degrees wouldn't qualify, but 90.0 would. And sometimes that's not quite obvious. So if you wanted to split it in, say, these, I would just go just a little bit less, so 89 for example. If we do a preview, it'll show us sections that fall within that limit, and it looks like somewhere here there might be one where that's not applicable, so we'll go 80 and we'll try that again. Yeah, so at 80 it'll split them up. Non-manifold edges, for example, is just if there was something in here. So let's say there was another triangle that was an invalid triangle. So if you look back at the edit video, it will consist of 3 points, but they all define a line, not an actual area of a triangle. That would be a non-manifold edge. So it by default it considers those as features that you want to split by. If we leave this and do an apply, it brings up some interesting options that we can do on a body level. This may be a case where you want to take the data and just create a new sheet over it or something like that. You can actually delete everything but target surfaces, and the way you do that is you click on a given body in this case. So let's take this one. It'll highlight in red. By the way, you can unselect with control click, or you can clear all selections with the escape button. Okay. But if we click this and then right click on it, we get the option to do some more things with this. And in this case, if you want to be just using this one sheet, you can delete others, and that will delete all but that surface or that body. So you could go ahead and export this and then work with that based on what you want to do with it. Other scenarios are possible too. You know, you can select multiple and then delete just those, or delete all the others, whatever combination you want to choose there. If we go back to our bodies and let's say we split them, and then we decide, oh, actually no, I didn't want to split them, I wanted to keep them together for something like we just did, you can just go in and use the merge tool. Merging does not combine them. There's not a true Boolean in that sense. It will just combine them all back into one data set. So it'll just say, okay, these are all the same thing. Yeah, let's go ahead and apply. And then it'll treat it again like one body. And we can go ahead and split them again using the split tool, and then do that. So those are the split and merge options. And those are generally quite useful for exactly these kind of scenarios where you bring in data and you want to work with one body at a time, which I recommend that when you work with larger assemblies and bodies, you individually work on them. You don't work on them as an entire assembly. In terms of larger body sets like this, there is an interesting tool which has got to do with the visibility of these. It's down here. It's a little eyeball. If you click on that, it'll bring up visibilities. Now, in this case, we have 149 bodies. So if you wanted to work with just the one, you can turn on and off visibility. Visibility is only what's shown in the graphics viewer. It doesn't say, you know, if you then run simplify on all bodies, it will only this will only hide them. But we can click on that, and you'll actually see a light blue box around the body in question, and you can go in, you can turn these on or off, and then click update, and it'll hide those from visibility. So that's a function there. Let's take a look at the actual Boolean operations. So these two are technically not Booleans. The Boolean operation does work on a facet basis. So for that, I'm going to import another file, and I've got this one here. We're going to split this into individual pieces, and that's just two shapes. These shapes are actually not particularly good, and they're actually invalid in some of these triangles, but that doesn't matter for this case. And we've just put our monkey mesh in between as an example for this. Go back to Booleans. This has been improved a little bit. It's not as good as some of the other Boolean tools out there. If you truly need to unite something or subtract something, I do recommend you work in your CAD application. That's a better place for that. I also know Blender is pretty good with Boolean operations. This here is just for convenience. It's probably not a tool that's going to be developed much further than this, but it does work for some very basic stuff. And generally, the idea is you can do unite, subtract, and intersect, just like most CAD applications do. The difference is here it's based on a set of cells, and it uses an SDF, which is signed distance function. It will determine whether something is inside one or the other or both. So it uses a function to determine that, and then generates a new body around that intersection data. It's fairly straightforward. So let's say we wanted to unite all three bodies here. Select unite here, and then we can select target bodies, and we click on these individually. And sometimes, especially with edge mode, sometimes the selection will be a little harder because it'll initially select an edge and then go, no, we don't want to select edges, and just skip selection altogether. So turning edge selection on and off can often help with these selections. So we got target bodies, we can clear them over here. Cell counts, be careful with the larger densities, these will take a lot longer, so default I'm just going to keep it 64. The SDF multiplier determines how much denser the function should be than the cell count. So generally leave that 1. If you find that this is something you want to do, but you see some of the intersection coming out strange, you can increase this to a factor of 1.5 or 2. 0.5 generally not very useful, but it can be applied if you want to see that. So we'll do the preview, and you'll see this is a very coarse grid. You get coarse results out of this as well. I am not quite sure how to get rid of some of these artifacts, but generally they can be edited out. If we turn in edge mode, we just see this is one large grid, and it just uses a function to determine whether something is inside or out. We can increase this somewhat. We'll go to 56. This will just take a few extra seconds. And when this updates, we do see that the resultant mesh is a lot denser, and therefore we also get back some of the more detailed sections. If we were to apply this, a lot of these little artifacts are not attached, so we could use the split tool and then select the body you want to keep and delete all the others. But we won't do that here. Let's do a subtract just to see what this would look like. In the subtract case, we have both target and tool bodies. So go ahead and clear this out. We pick this as our target. I'm going to turn edges off. This is our target. And then we switch over to our tools, select these two. And if you toggle back, it'll show you what's within those selections, okay? We're going to keep this a little bit rough. Go preview, and then we see it basically just chops the sides away. Again, not super accurate. It's based on how the algorithm works. It's just not going to give us very clean intersection lines. So be aware of that when you use this. Lastly, the intersection algorithm basically says what is part of one body and the other, and so on. So beware, if you were to pick all three bodies here, the result is nothing, because there is no intersection point of all 3 points. So we can unselect this, we leave it at 64, and then we can see this is the section that overlaps between those two bodies. We can make this a little more refined maybe. Let's go one further. So you can see that this is that intersection of those two bodies. If we go back to the previous one, just so it's a little quicker, we can play around with this a little bit and see how that affects some of these artifacts a little bit. Keeping it coarse will generally add more, just because the overlapping mesh is coarser. Future versions of this may address it. If this is truly a tool that people use, let us know. We can put it on the list of things to improve upon. But generally, this is about as good as you're going to get the data out of this. And then apply. If we do that, we get the body back that actually was created. The other one wasn't affected, so it doesn't get deleted. So in this case, what we may want to do is select this, split the body, apply that, and then we have all these little artifacts that we don't want. We may want to keep this body, so what we do is you select this, and then do delete others, and then anything that wasn't selected gets deleted. In this case, we basically end up with a fairly clean set other than this artifact, and we could go back and manually edit this out. But that's basically it as far as the Boolean operations on this. So this video covers the bodies within the InStep application. Next time we're going to start looking at the reverse engineering tools.